Experiment. Meet Captain Quantum.
And here we are, the granddaddy of all quantum weirdness, the infamous double slit experiment.
The first people who did these experiments, and these experiments of, crude experiments of this kind, were first performed almost 50 years ago, or more, 60 years ago. Those people were flabbergasted.
To understand this experiment, we first need to see how particles, or little balls of matter, act. If we randomly shoot a small object, say a marble, at the screen, we see a pattern on the back wall where they went through the slit and hit. Now, if we add a second slit, we would expect to see a second band duplicated to the right. Now, let's look at waves. The waves hit the slit and radiate out, striking the back wall with the most intensity directly in line with the slit. The line of brightness on the back screen shows that intensity. This is similar to the line the marbles make. But when we add the second slit, something different happens. If the top of one wave meets the bottom of another wave, they cancel each other out. So now there is an interference pattern on the back wall. Places where the two tops meet are the highest intensity, the bright lines, and where they cancel, there is nothing. So, when we throw things, that is, matter, through two slits, we get this, two bands of hits. And with waves, we get an interference pattern of many bands. Good so far. Now, let's go quantum. An electron is a tiny, tiny bit of matter, like a tiny marble. Let's fire a stream through one slit. It behaves just like the marble, a single band. So, if we shoot these tiny bits through two slits, we should get, like the marbles, two bands. What? An interference pattern. We fired electrons, tiny bits of matter, through. But we get a pattern like waves, not like little marbles. How? How could pieces of matter create an interference pattern like a wave? It doesn't make sense. But physicists are clever. They thought, maybe those little balls are bouncing off each other and creating that pattern. So, they decide to shoot electrons through one at a time. There is no way they could interfere with each other. But after an hour of this, the same interference pattern is seen to emerge. The conclusion is inescapable. The single electron leaves as a particle, becomes a wave of potentials, goes through both slits, and interferes with itself to hit the wall like waves.
Let's make sure we understand this double slit experiment so far. When we shoot matter, like a BB or a marble, at a barrier with two slits, we get two bright streaks on the screen behind in line with the slits, like this. And when we shoot waves, like waves of water, through a barrier with two slits, one wave becomes two waves on the other side of the barrier, and when two waves hit, they interfere with each other. If the top of one wave aligns with the top of another wave, it's called constructive interference, and the result is a new and bigger wave. But if the top of one wave aligns with the bottom of another wave, it's called destructive interference, and the result is that they cancel each other out, and there's no wave at all. And when constructive and destructive interference happen together, you get an interference pattern on the back screen that looks like this. Now, if we shoot an electron, which we have always thought of as a particle, a little piece of matter, through a barrier with two slits, you would think we would get a pattern on the back screen that particles make, like this. But we don't. Instead, we get an interference pattern that waves make, like this. The conclusion is that electrons, which are the building blocks of what we call reality, are not solid particles at all, but exist as waves as well. In this wave form, they are called quanta, which is why the study of how they behave is called quantum physics. But that's not the end of the double-slit experiment. Let's rejoin Captain Quantum where he left off.
The conclusion is inescapable. The single electron leaves as a particle, becomes a wave of potentials, goes through both slits, and interferes with itself to hit the wall like waves. Physicists were completely baffled by this, so they decided to peek and see which slit it actually goes through. They put a measuring device by one slit to see which one it went through and let it fly. But the quantum world is far more mysterious than they could have imagined. When they observed, the electron went back to behaving like a little marble. It produced a pattern of two bands, not an interference pattern of many. The very act of measuring or observing which slit it went through meant it only went through one, not both. The electron decided to act differently, as though it was aware it was being watched.
So the electron is very peculiar. The electron is very peculiar in the sense that when you are not looking, electron can be here, can be there, or can be over there in the corner of this room. It can be all over this room, so to speak. But whenever we look, this is the strange thing about these electrons. Whenever we look, we always find them to be in one particular Geiger counter, although we may have a room full of Geiger counters. We never hear the Geiger counter sticking all over the room. This is the fundamentally important stuff about the